In section 3.3, we're going to be learning the derivatives of the trig functions. And pretty much anytime we move on to a new sort of function at this point, we have to fall back on the limit definition of the derivative in order to come up with a formula. Once we know the formula, then we can use some of our shortcuts. As we evaluate the limits that are going to show up when we try to find the derivatives of sine and cosine, which are the two that we're going to start with, there are a couple of limits we're going to need to know. The first of these is the limit as x goes to 0 of sine x over x. Now, it's not obvious at this point why that's going to be relevant. I'm just telling you that it will be relevant. We are going to want to know this. Notice this is an indeterminate form. Pretty clearly the bottom is going to 0. Sine of 0 is 0, so the top is also going to 0. So we've got this indeterminate form. It does not look like we're going to be able to factor and cancel because neither of those things factors. Each is just a single quantity. And it doesn't look like we can rationalize and cancel because there are no roots to rationalize. We're going to end up using the squeeze theorem, but in a way that's not particularly obvious. Because while it's true that sine of x is bounded between -1 and 1, that actually isn't a very good starting point for us here. Because look at what's happening. As x is getting close to 0, dividing by something small just makes something really, really big. Okay. So that's going to take things that are nice and bounded and essentially make them go off to infinity instead. Okay. So that's not going to be particularly helpful. Just like with the derivation of the product rule, as I work through figuring out this limit, you're not responsible for trying to guess what I'm going to do or understand what my motivation is. You're just responsible for being able to understand that what I'm saying is true. What we're going to do is we're going to use a picture here. I'm going to draw the unit circle, and I'm going to draw x as a small angle. It's going to be close to 0. I'm going to choose to make x a small positive angle, so that that's going to put it in quadrant 1. Okay. Now, because of that, we're going to actually be working then with the one-sided limit as x approaches 0 from the positive side of sine x over x as we use this picture. By being in quadrant 1, everything's positive. My angle is positive and all of its trig functions are positive. Now, if we were in quadrant 4, which is where we would be if x was an angle close to 0 but a negative angle, then x would be negative and some of the trig functions would also be negative. It turns out the two-sided limit that we get, it does exist. It's the limit from the right is the same as the limit from the left. But the geometric argument that we make has to be modified if we're working in quadrant 4 to account for the fact that certain things are negative there. So I'm going to just work out the limit as we approach from the right, but I'm just going to tell you, fact, the two-sided limit is the same. All right. Now, what I'm going to do here is I said this is the unit circle and here's my angle x. Since I'm calling the angle x, I usually label my axes as capital X, capital Y, so that I don't confuse the capital X value of a coordinate of a point with x, the angle. And let's just remember that if this is a point on the unit circle, this distance is 1, that's a radius of the unit circle, and this point right here, capital X, capital Y, is equal to cosine of my angle little x, comma, sine of my angle little x. Those are the unit circle definitions of sine and cosine. Okay, now this is going to be a geometric argument. What I'm going to do is I've already got here a sector. That would be this little slice of pizza that I've got created by the angle x. I'm also going to create two triangles. I'm going to draw in a secant line, like so that I've got this little triangle right here. And then I'm also going to draw in a vertical line here and extend this ray, the terminal ray of angle x, to create this larger right triangle. So let me just add some shading here. Okay, so the small triangle that we've got right here, I'm just going to shade that in blue. Okay, then the sector contains that piece, but also what I'm shading in red here. It's like the blue is the slice of pizza without the crust, and the sector throws in the crust. And then this big right triangle, you'll notice it completely contains the sector, but it also contains what I'm shading in green right now. And for any angle x that would be in quadrant 1, I could create a picture like this, where I had a small triangle contained inside of a sector, contained inside of a bigger triangle. So that's what we're going to use for the squeeze theorem. So my inequality is going to be that the area of the little triangle is less than or equal to the area of the sector. Now I'm saying less than or equal, okay? Clearly it's actually strictly less than. But I'm ultimately going to be using the squeeze theorem to take limits, and I'm kind of hoping that when I take limits, I get equality of things. Okay, so I'm just going to use inclusive inequalities here. And this is less than or equal to the area of the big triangle. So, just to draw in our pictures, here's our little triangle. And I can draw 3 copies of that because that's contained in the other 2 shapes. The sector adds on to that. It adds on that crust, that red area. And that crust or that red area is contained in the big triangle. The big triangle adds on that extra green portion that we have right here. So there's our lovely inequality. Now, what we need to do is we need to come up with algebraic expressions for each of these 3 areas. So let's do that. Okay, for this little triangle, I know that the area of a triangle is just 1/2 the base times the height. So I want to try to figure out what are the base and what are the height. Okay. Well, I can take the base as this length right here. Now, if I look at this picture, that's going from the origin to a point on the circle. Oh, well, that's a radius of the unit circle, so that's going to be 1. So the base there is going to be 1. Now, for the height, I want to remember that the height is going to be this perpendicular distance. It's this vertical distance. It's not one of the side lengths here. It's just going to be this distance here. If I draw that in on this picture, I can see, oh, well, if it's the vertical distance to this point, that's just the capital Y value of that point, which is sine of x. Now, this is why I've chosen to be working in quadrant 1. If we were in quadrant 4, sine of x would be negative. And so the height of my triangle, I would have to adjust by taking the absolute value of sine of x. But here, I can say, we're just working with, in quadrant 1, we've made that choice, and so we get sine of x. So 1/2 times 1 times sine of x is just going to give us sine of x over 2. That's going to be less than or equal to the area of this sector. Now, for the area of a sector, I have to remember how we figure that out. Well, I'm really thinking of that as this is just a fraction of the area of the entire circle. Okay, so let's see. I'm just going to write it here and then I'll erase some of my work because I'm going to need this space again. But I can say this is going to be a fraction of the area of the circle. Now, the circle was the unit circle. Area of a circle is pi times the radius squared. So that's pi times 1 squared. That's just pi. Now, what fraction do we get? Well, that's where the angle comes in. Because I can think of this angle as it's part of a rotation. If I were to rotate all the way around, the angle that would correspond to the full circle would be 2 pi. So the fraction that we get is just x over 2 pi. The angle that corresponds to the sector divided by the angle that corresponds to the full circle. Those pi's cancel, so the area of the sector is just x over 2. Excellent. All right. So now I need to figure out the area of the big triangle. So again, because I've got this small board, I've got to erase that work. All right, working with the big triangle, I can say, okay, well, I know the area of a triangle is 1/2 the base times the height. Now, the base of this triangle is just this side. That's still 1. It's the same base we had for the smaller triangle. The difference is in the heights. So I can go ahead and fill in that 1 there. And now I need to figure out what the height is. I'm just going to draw this triangle again up here. What we've got is here's our angle x. We know this side is 1, and we want to solve for the height. So there I've got an angle, the opposite side, and the adjacent side. I'm thinking tangent. Tangent of x is opposite over adjacent. So the height here is actually equal to tangent of x. And again, because I'm in quadrant 1, I know that that's a positive number, so I know that's a legitimate value for a height. I would have to adjust with an absolute value if I were working in quadrant 4. Okay. All right. So 1/2 times 1 times tan x, that's just going to be tangent of x over 2. All right. This is a long derivation. This video has been going for a while. I'm going to stop it, clean up the board just a little bit. We're going to pick up from here in the next video.